My name is Khuri Yakub, and I'm chairing the first session this morning, and I'm also have the other hat of making a short presentation about CMOTs and all the crazy things we want to do with them, 2D arrays in imaging, therapy, and neuro, given that neuro is simply therapy at a lower power level. So I'm just trying to keep track of what I'm doing. Okay, so what I'd like to start with is, this is the outline of the presentation. I want to give a short description of the CMOTs, what they are and what are their advantages, and then talk a little bit about the electronic integration, which is inherent in their ability to be used for integrated imagers, if you wish, and of course integrated maybe neurostimulators or integrated HIFU devices where you can shrink the size down to something that you can imagine even implanting. I'll talk about the HIFU capability of the CMOT and why we think this is relevant, important, and advantageous over piezoelectric systems. And then, unfortunately, we also have to have the back-end system required of us, because we can't go out there and buy a back-end system to do what we want to do, especially if we're using a 2D array of any sort, shape or form that is out there. Then I'm going to show some examples of some new ring arrays we have made for endoscopic imaging, anatomic and photoacoustic imaging. I'll show you some results and some interesting challenges that the photoacoustic application presents that we need to resolve. And I'm going to talk about 2D arrays with a single ASIC capable of imaging, HIFU, and therapy, and then a variation on this solution where we actually use a stacking of 2D arrays with interposers, just because the power requirements become too tenuous to handle with just a single chip that you want to put against somebody or in somebody that consumes so much power. And then I'll make one very simple conclusion and thank all the people who pay for this. So what's a CMOT? So this is an example in here of actually, this was a HIFU device. CMOT is, you take it's a capacitive micro-machined ultrasonic transducer. So it's capacitance instead of piezoelectricity. So we have a capacitor with one plate that is flexible and that can vibrate under the application of voltage. And then it's made, it's micro-machined. So this is built in an integrated circuit fabrication facility, and that presents all the advantages of IC manufacturing in terms of control, reliability, scaling in small or large in size and dimensions, both horizontal and vertical. And it's ultrasound, so that we can go in frequency, actually all the way from maybe 10 kilohertz to 100 megahertz, and they're transducers, they're reversible, they can transmit and receive ultrasound as one would like to see. The main reason why CMOTs really work is because you can create a large electric field in the cavity or in the gap of the capacitor, and that translates directly into electromechanical coupling coefficient. So when you want to compare it to a piezo, it simply is getting an E field of 10 to the 8 or 10 to the 9 volts per meter in the cavity, gives you everything that you want. It's also the Achilles heel of the CMOT, because operating with high electric field can induce charging or breakdown, and those are the two most important aspects that you need to control. So you have something that is very potent, but because of that potency, it's also difficult to control. It has a very interesting advantage in working in water. In working in air, it's perfect, because at resonance, these plates vibrating into air have very low impedances, mechanical impedances, and they're perfectly matched for operating in air. But when you load them with water, water is very heavy compared to the plate. So effectively at resonance or around where you're operating this at center frequency, the plate properties are practically not important, because you're mostly pushing water up and down. And that, because it's an overdamped system, you end up with very broad bandwidth, which is the traditional aspect of CMOT that is most focused on. This is what I described earlier. You can operate at different frequencies. Making 1D, 2D, or any shape array is just a simple matter of photolithography, and that's simply defined by, making a mask and exposing photoresist and what have you. And we can do any in various sizes of devices. We've made them ourselves from 100 micron by 100 micron devices up to a whole 4-inch wafer being one device. But the 4-inch also is only the limit due to our own fabrication facility. You go into a 6-inch, 8-inch, 12-inch. Today, people talk about, 45 centimeter silicon wafers. I don't know what that is in inches, but you can imagine things are growing. And this is the IC fabrication aspect of it. It shows examples of some of the other engineering, let's say, controls that one has while making a CMOT, and that has to do with how you can shape the cavity. Here is a device that's operated while the plate is in constant collapse. This is the same thing, but we've isolated the center island in here, and so that electrically it's no longer involved as a parasitic capacitor in there, but it presents some other advantages. I call this blob in here the world's largest EEPROM, but that's for a different type of thing. This is another way of implementing CMOT where you actually have something like a platform over silicon posts. The silicon posts operate as the springs, and this is a typical operation of a device like this. You get something like 1.5 megapascal under these conditions with very nice broad bandwidth and very good operation. And what you see in here on top is something like a honeycomb structure that we put in this vibrating plate to manipulate the stiffness versus the density of the plate and control where the resonant frequency will be and what have you. So this is again showing the sort of the deep reactive ion etching, defining these long posts that end up basically being the spring of that device. So overall, this is a very nice platform, and we've done a lot of these applications that we've used. I'm only going to focus on the medical imaging and therapy aspects of this today. But as I said earlier, we have quite a bit of work on using these for airborne applications. Gas flow is a huge application in terms of billions of dollars of market size. Gesture monitoring for interacting with computers and screens and so on is also a billion or several $billion industry. Wireless charging is a very interesting application, again, for the technology. So there are quite a few airborne interesting things one can do with this. So electronic integration is something we visited for about 10, 12, 15 years now from the beginning. This is some of our earliest attempts by creating through-wafer vias in the silicon, bringing contact to the back, having a fully populated 2D arrays on top, and then a solder bump to connect to an ASIC in here. And this solution is still something we use today continuously. This is a result of a collaboration with General Electric, where the idea was to tile a very large number of 16 by 16 arrays, where you get the yield, to end up with something of the order of 10 by 10 centimeter breastplate for 3D breastplate imaging and HIFU. And here we use an interposer between the CMOT and the electronics, and that allows you to basically vary the dimensions of the ASIC that you use on the back side. It allows you to put maybe more power in there that you can cool, if you wish, down here and keep it, or down here, and keep it separate from the contact with the individual that's getting the treatment or that is getting imaged or diagnosed. The most interesting, and another very interesting way of doing this is to actually have the whole CMOT built. In here, I'm showing this done by bulk micromachining or direct bonding. It can also be done with sacrificial release processing, and I suspect maybe Levent or will mention that. But we can actually do things like this, where you get your CMOS done, and with 2 masks only, you can bond at about 400 degrees centigrade and a wafer, and with the MOS wafer, not MOS wafer. It escapes me now. Anyway, we can bond the wafer to the top and then form the plate and finish the device with only 2 mask processing. So let me also say a few words now about the ability of CMOS to do HIFU. Typically in HIFU application, what you're trying to get is something of the order of 20 watts per square centimeter at the face of the transducer, and then you use focusing gain to deliver the much higher powers at focus to do your burning. And it's plus or minus this, but this is sort of a nice number in the mid-range. It's a high energy application because as opposed to medical imaging, where you excite the transducer with a pulse, you're using quasi-CW excitation over a number of cycles, where the treatment could be in times of the order of seconds. And you'll hear 2 more talks about HIFU later this morning. You want to be efficient. You want to couple all the electrical energy to mechanical. You don't want to add a lot of reflection because you don't want to provide too much power and what have you. The most important problem here with the piezo is they tend to get hot because the dielectric loss tangent in piezoelectric materials. So you need active cooling of the piezo. That's something we don't need with CMOS. And then you need operation over the various frequency ranges. Typically, we want arrays to do HIFU, and then these are the other attributes that one needs for this application. This is a sample result of what we can do. This is a CMOS device in an MR showing that's MR compatible. This is showing the ability to get up to 1 megapascal output pressure continuously. This is the device running for an hour, basically continuous, non-stop, with same output pressure, 1.6, 1.7 MPAs peak to peak. And this shows that a 6-degree temperature rise, 6.5-degree temperature rise. So you can operate them because there are no loss tangents in there. The mechanical Q of the device is very high, very huge, so you really don't get any self-heating. The one important aspect of this, and Professor Atalar will say much more about this later, when you operate these devices in CW, is the mutual impedance between the cells, or cell-to-cell corresponders, or talking. And the reason why that becomes very important when you're doing HIFU and CW operation, because you can set these types of crosstalk effects in very nicely, and during your operation you can end up at frequency where there is practically zero output, because some plates are vibrating at one phase and the other at an opposite phase, and you end up losing the energy that you're trying to get out. So let me show you where we're at with some of our 2D array work. We have 2 projects for HIFU with 2D arrays. One of them, I'm showing a wafer in here. This is an array of 40 by 40 1 millimeter elements operating at 1 megahertz. And we have it made in 20 by 20 that we can dice in case we lose some of them, then at least we'll have some harvest. This is showing input impedance operation of these devices at low frequency. And this is showing the layout of the 20 by 20 transducer elements. But the way we want to operate them for HIFU applications on these 400 elements, we only want to use 8 phases to excite them instead of using 400 phases. And what you see, the coloring in here corresponds to like 0 degrees, 45, 90, and so on as you go around. And so we go from here into a PC board that connects all of the colors together, so we end up with the 8 phases coming out of there. And this is a simulation that indeed you can do F1 focusing very nicely, and we also have simulated these for HIFU and temperature rising and so on, and actually it works very well. We recently sent the PC boards to a company to put solder bumps on these, and once we get the solder bumps, then we will flip chip bond the wafer on top of this, and we'll have a 1 megahertz, either a number of 20 by 20 or the full 40 by 40 2D array for operational. Eventually, of course, you want total control over the 400 elements, so you can HIFU and steer at the same time without the fixed focus that this original implementation will show. Here what I'm showing is the fact that because we're doing things where you can't go out and buy a GE imaging system or a Siemens or a Philips or Samsung maybe, who knows, anywhere, somebody else's, we need to get into things like platforms from either Verasonics. We have another platform from Cephasonics, and mostly what they are pulsar receiver, FPGAs, and a lot of memory, and then we program them to implement whatever solution we want for imaging. And this is an example of a ring array that we have made for an endoscope. This is 1 centimeter on the OD, 5 millimeter here on the ID, so you can imagine then having a large lumen through which you can do a lot of things. And then for testing purposes, we are connecting first each one of these rings alone separately to a number of ASICs that we have made, and we test it for both imaging and photoacoustic imaging. And this is now imaging a spring in here, and you can see it display in there with maximum projection. And we like this type of display because it allows you to see exactly what it is that you've done, and so you can see the image forming as you cycle through this. This is running at 11 frames a second right now because of the large size of the field of view that we're using and the number of elements. We also do photoacoustic imaging with this, and this is now the photoacoustic image of this phantom overlaid on over an anatomic image. So this is the anatomic image here, this is photoacoustic, and this is the two. And what you will notice in the photoacoustic image actually is that very large side lobes of the three phantoms in here that are light absorbing. And that's important, and that's a problem we're starting to work on right now. The reason for this is when you do imaging with the ring array for anatomic application, we use something called Norton weightings. And so you weigh the aperture as you transmit, and in receive, there is no such weighting. So we're working actually trying to figure out the theory of how do you do weighting on receive to try to reduce the side lobes in photoacoustic imaging in this part. So now let me talk about 2D array. This is a 32 by 32 integrated 2D array that we have. And what you see in here are the yellow elements in here are the transmit element. The diagonal elements are used for receive. So we have 64 receiving element and 900 and whatever it is, 60 transmitters. This is operating at 5 megahertz. Each cell in here is 250 by 250 microns. And we have through wafer vias to flip chip bond this to an interposer, or on top of the ASIC directly, actually. It has transmit beamformer, as I said before, and it also is capable of doing 4 multi-beam transmit, 4 beams at the same time to speed up the imaging rate, so we can increase the imaging rate. It generates pulses, high voltage pulses up to 60 volts, and the 64 receive channels. What we figured out in the last few weeks is that we can actually fool this ASIC, which we originally designed for imaging only, and make it operate in CW, which means we can get it to put out tone burst and do beam forming on transmit with tone burst with 64 elements, and the whole thing exists. So effectively then, one can do imaging with this, one can do HIFU, which is with this tone burst, and the neuromodulation, you just back off on the voltages. Instead of going up all the way to 60 volt, you use a lower voltage, and then you can do the stimulation. The interesting part of this is this whole array and the ASICs are 1 millimeter thick. It's 1/2 millimeter thick ASIC, 1/2 millimeter thick CMOT, and a little flexible PCB that comes out of it. And so you can let your imagination run wild as to how you can use something like this in a number of applications, similar to what we heard yesterday, whether you put it on the brain of an animal, of a rat or a baboon or something like this, and do stimulation anywhere. This is an exact picture of the die now. This is the ASIC with all the solder bumps on it. My battery is running away, but you can see solder bumps in here, and this is the ASIC. And it's 9.2 by 9.2, and I should acknowledge Intersil in here, that actually we designed these things, we tape them out, and they give us the silicon for free. So that's a very nice relationship. And this is what it looks like. This is a real picture of the CMOT itself, and the ASIC flip chip bonded on top of it. And this is the picture on top of the elements. This is the backside, where before they got solder bumped to the ASIC in there. And this is a quick image of a phantom in here. We had a little issue. This is 5 volumes per second real-time imaging. If we do 4 beams on transmit, we can take this up to 20. This particular ASIC had a slight issue, which has been fixed, and the new ASIC just arrived, where one of the DC lines had too much IR drop on it, and so we couldn't use it to its full potential. But as I said before, we tested it for CW, and this just to show you an example that indeed these things can provide CW. This is up to 16 volts. I can't see very clearly. But the most important aspect of this right now we're looking at is when you operate this for imaging, the total consumption of the chip is a few hundred milliwatts. But now when we're running at CW, our rep rate or our duty cycle is much different, and so we take a huge beating on power, and so we have to figure out how to do this with a lot less power consumption. And so this is now the other solution we're doing, is that where we take the CMOD, we interpose in here a switch ASIC. And so this switch ASIC right now has been designed, is being taped out, and will be fabricated for us by Maxim, again for the same price of $0. And then we sold through FRVIAs in the switch matrix, we can then connect to the ASIC, and now we have an integrated solution where we can play, whether we directly put the ASIC to that, or we have something in between to switch between therapy or between the imaging modalities. I think I'm up to 20 minutes, so I should be a good chair and stop in here. Steve showed you this example yesterday. Just quickly, I will show you, we have a project on putting a CMOT array on a pill like this. These are a capsule endoscope, and this is our simulation of what one can do with imaging with something like that. The interesting thing about a capsule endoscope, if you unwrap it, you get a Band-Aid. And I'll leave it at that. So I'll just close by saying that, you know, what the flexibility of the technology and the electronic integration, I think there's a huge number of applications of things we can play with. Thank you. Questions? Yes, Vera.
What is the frequency band with each device? So each CMOT array operates at one frequency or any frequency?
So typically they're about 100% fractional bandwidth. So the 1 megahertz device, we can run it anywhere from 0.5 to 1.5 megahertz if you want CW. So the idea would be to then come out of here into a switch box and maybe an inductor box to sort of tune it for the frequency of operations, and then to the power supplies, right? So at least for high-flow application, that's how I see them. But we can certainly tune them over a very broad range. We're also doing the same construction of an interposer board for the 32 by 32 array at 5 megahertz to bring in out 8 channels and then do HIFU in the middle of a volume image. And then we see that as a first solution to sort of combine the two, where you HIFU and then you have a 3D volume and then you move the array manually to change the site of the HIFU, but the imaging is done over 3D. But that's a more 3D PC board to make, so it's more difficult to make. Yes?
You mentioned the interfacing CMOS to the back end of a common system as a challenge.
Right. No, so what I mean by that is that if you look at the 3D imaging systems on the market today, the GE, Siemens, and Philips, they have a handle, like it's my understanding the Siemens has 11 ASICs of their own inside with a number of FPGAs in the handle. And so if you have to basically plug your technology into all of their electronics. You can't do it yourself. So you can't buy the system and say, okay, I made a 2D array of Siemens and I'm going to plug it into it, because you need to know what the rest of it is. That's part one. Part two, your design of the preamps that will go in there has to be different to get better noise performance, because the impedance that the CMOS presents to the receiver electronics is different from the impedance that the piezo presents, and that has its own challenge. So we design for slightly different noise performance, current noise, voltage noise, and things like this.
What about the issues of channel reduction? You have very large numbers of...
So this is, so our approach to it was to do the transmit beamforming, dedicate transmitters and receivers. And for the 1024 channel, that means we address them digitally by delaying the firing of all the elements. So we address them in 2 to the n fashion as opposed to n squared. And so we have maybe 100 cables or less to pop the whole thing. And that's at least our approach to it. We end up losing a few 7-8 dBs on SNR, but the point spread function is more or less the same, and the performance is actually quite good. But we take a beating on that because we can't have 1024 cables coming out of that. Yes?
So what kind of SNR can you obtain, say in a normal fashion? How deep down can you scan these?
So the volume images I showed you, we're going in 7-8 centimeters with an 8.2 by 8.2 millimeter array. So 8 millimeter by 8 millimeter, we're going like F10.
Another quick question. The fact that you were able to fool your ASIC to allow you to do continuous wave
Right.
or burst mode would suggest that you could do RF type techniques with the same transducer that you're going to do imaging. Is that right?
Yes,